I'm joined by Noah Greer to present our project proposal for the class. To give a bit of context, we work for an electric marine propulsion company in Orlando and have begun exploring the feasibility of additively manufactured heat exchangers in marine applications. We currently use heat exchangers for thermal management in our batteries, motors, and power electronic systems. And whereas most EVs utilize refrigerant cooling for heat rejection, we use the abundant and near infinite source of cool water below the boat to reject heat. The setup is simple, but has one major drawback. The temperature delta between the coolant and fresh water is small and requires the use of high-efficiency plate heat exchangers, typically constructed of copper or nickel-brazed stainless steel plates. With metal 3D printing commercially available and relatively low cost compared to years past, additively manufactured heat exchangers are now entering value viability. When compared to plate heat exchangers, additively manufactured gyroidal heat exchangers offer comparable and potentially better performance for similar price without the drawbacks of potential corrosion of the brazing filler.
What we found while digging into this subject is that published research regarding where the flow transitions take place has been heavily focused on computational studies. The experimental studies we were able to find did not focus on validating this transition area, and instead were focused on correlating pressure drop or heat rejection with computational models. And we believe that this leaves an experimental validation gap that we can fill with our work. Our main objective for this project is to experimentally validate computational studies. To do this, we will sweep Reynolds numbers on a lattice in a water tunnel while observing how the behavior of the flow changes as the Reynolds number changes. These observations will then feed into comparisons with the published computational studies. And finally, we will be able to use the results of this experiment for our own simulations as we explore the viability of 3D printed heat exchangers in the electric marine space.
For these experiments, we will create a lattice geometry of interest using an SLA printer and clear resin. By using a fluid with similar refractive properties as the cured resin, like corn oil, we'll be able to see into the geometry with minimal visual distortion. Our first experiments will involve the use of dye visualization, where dye is injected into the flow field and the behavior is observed. The use of a high-speed camera is required to fully capture the fluid behavior due to the increased fluid velocities in microchannels. If time permits, we are also considering PIV, or particle image velocimetry, to directly measure the planar velocity field in the structure. PIV utilizes a line laser projected through the clear lattice structure and creates a planar cross-section through the object, similar to how an MRI or CT scanner images. The fluid behavior is recorded and post-processed through an open-source PIV software called OpenPIV. The image on the right shows an example of what PIV would look like after it's been post-processed through OpenPIV. The output is a planar vector field which shows the direction and magnitude of the suspended particles, which are assumed to follow the flow field. We found similar studies that have utilized this method with good results. The top image is a clear SLA printed part with a cavity filled with a refractive index matched fluid. The phantom model is almost completely transparent with minimal optical distortion. The bottom image partially shows what the cavity looks like and is a snapshot from a longer video recorded for the input in our In our case, OpenPIV actually utilizes machine vision to detect particle position changes between frames and generates a vector field based on the magnitude and direction of the change.
Now here's a system layout and flow diagram for dye visualization. The setup pumps fluid into an elevated tank, which creates constant pressure and flow that feeds into a flow meter and test lattice. Dye is injected just upstream of the test structure, and a high-speed camera is used to capture the test and is slowed down for slow motion analysis. It was a similar setup, but it introduces a laser sheet projector in the observation step, along with flow media to scatter the laser light. The usability study we performed earlier this week. Our goal was to see if we could make an entirely 3D printed water tunnel to test pressure drop across a lattice at the two clear tubes. Based on this limited test, we believe that we have the skills and tools necessary to complete the study successfully.